Okay, I'm going to post this out in response even before I look at the problems that I picked up today from some of you, and let everyone else know that there were due today. Let's see if we can do this. If I go to review, start inking, there were, I think, maybe 8 problems. Okay. Now, many of those, I'm hoping that maybe after today or maybe after Wednesday, you can see that each of those problems, to get a solution, should not be a whole lot of time if you go by this. Concurrent force problems, you draft them up kind of like a point. You show all your vectors. I think the first problem was something like a force there, and maybe a force there, and a force there. And you add them up tip to tail, which means that you use the rule of transmissibility in that free body diagram. Let me draw my coordinate system here, x and y, in a positive moment, which means that you use the rule of transmissibility and you go ahead and slide this one through, and you slide this one through, and you slide this one through, and you add them up tip to tail, which means that you take, in the x direction and in the y direction, you take force 1 times the cosine of theta 1, force 2 times the cosine of theta 2, and force 3 times the cosine of theta 3, where thetas are the directions from the standard position angle, which is the x-axis, standard position angle. And for the y's, you add up. Well, let's see if we can get this pen working again, which we can't. You add up F1 times the sine of theta, F2 theta 1, F2 times the sine of theta 2, and F3 times the sine of theta 3. And so when you do that, in a problem like this, which was the first one given, you more or less are getting the sums of these two forces, and in reality what's going to exist is a reaction force that's going to be equal and opposite, because really we're heading to that point where you want to look at something and say the sum of the forces is 0. There is another problem that looks something like this. It's showing you with a certain amount there, there's a truss coming in there, and you've got an amount of force, I think, coming down this way, and you have a reaction force here in this direction here and over here potentially. But here's the reality with this. When you look at this particular force, the sum of the forces at this point is 0, and once again you now show that this way. You have a reaction force there in the y, a reaction force there in the y. You take this one and push it through, and you go ahead and you take this one through as well, and that is that force there. And you start with realizing that none of these can be greater than 7, and so in effect, if you look at this here, if the sum of the forces is 0, this is the member you're worried about typically, because this, in order to have 7 this way, right, this is going to have to be pushing with 7 back in that direction, which means it's going to also have to have a value coming back this way. So that is a concurrent force problem. Let's see if I can go ahead and erase this, or at least move it up. See if I can get up here and move this over. All right, so we're still within our constraints. So I'm going to go to this, go to a new one, and let's see, we'll go ahead and, what is it, Control C, Control Z, right? And I'll just kind of use, hopefully, review here. I'm going to start inking, and I'm going to go through here and do a blank slide. All right. Concurrent force problems. There are some others as well, but realizing the first 3 problems, the form of problem is the concurrent force problem. And you do concurrent force problems by For instance, there's one that looks like this. You have a known value there and perhaps another one there, and it tells you that I think these things are equal. And so all of a sudden, instead of having the sum of the forces in the x equal to 0 and the sum of the forces y equal to 0, two equations in a two-dimensional problem, you also have T1 equals T2. You have a third equation. And so as you look at this problem here, the solution tends to be something like this. It's coming back this way, and then you're going to come back along two directions to get back to vertical. So that is another one of these problems. And this one is probably better solved mathematically by realizing that you have to know the direction of this, the direction of that, direction of each of these. And the direction is off the standard position angle. So you're going to very often end up with a set of lists that look like this, right? F1 times the cosine of theta 1. F2 times the cosine of theta 2. F3 times the cosine of theta 3. F4 times the cosine of theta 4. This is in your f of x column, your f of y column. And if you remember, we're just dealing with t. We're dealing with the two-dimensional system, because in reality, f in the x direction is f1 times the, you remember, the cosine of phi times the cosine of theta. And f2 times the cosine of phi 2 times the cosine of theta 2. Remember that 2D, 3D? That works for concurrent forces. All right, I'm going to go through now and grab, hopefully, we talked about in class today, right? This problem, there is a wrench here. That's a radial vector, and that's a force vector. This has a direction equal to that angle. This has a direction equal to that angle. They each have I, J, and K components. We know that the moment is equal to R cross F. R cross F can be thought of many ways. It's the magnitude of R times the magnitude of F times the sine of the deflection. Hi. It is also the magnitude of the R times the magnitude of the F times the sine of the direction of the force minus the direction of the radial vector. It is also force times orthogonal distance. It is also the determinant of I, J, K, R in the X, R in the Y, R in the Z, F in the X, F in the Y, F in the Z. It is also equal to, if you would, that area there. That was just to determine the torque. The one before that we did in class. I won't do that in these 10 minutes. I'm going to go to a new one here. Realistically, this rock problem, it's not complex. It's to realize that how do you eat an elephant? One step at a time. And so you have essentially, when you have that rock problem, if you would, not an eye rock problem, but I'm going to make my rock a little bit bigger there. It's tipping about a point here. Its weight acts down, and you've got a crowbar here, right? So what you have to do is break that up into two free bodies and think about the fulcrum here. And what you have is force times distance equals force times distance. And you can do it by radial vectors or not, but that's a force times distance equals force times distance, and that will get the force here. That's the force of the bar on the rock. And then you draft, and once you determine that force of the bar on the rock based on distance from the fulcrum or the spinny point, you're then going to do another free body diagram of the force of the rock on the bar and draw your force times distance equals your force times distance. Those can also be done by R cross F. So that's what I'll put out. It's 10 minutes. I'm taking the time off this afternoon with my daughters. Was going to do this in a coffee shop, but I don't have this really cool squiggly bit here. So I will do this again after I look at the problems. But understand that you had two types of problem. concurrent and non-concurrent force problems, and then that idea of breaking things up into smaller cascading free body diagrams is something that many of you might have missed. Thanks for listening. See you tomorrow.